So the third part of this problem would introduce pressure drop. And they just ask for a plot of the conversion versus the pressure drop as a function of the PFR volume. And so that would give you, and it tells you that the alpha is 0.001. And it tells you to solve for the conversion at a volume of PFR equals 500 cubic decimeters. So have you guys used polymath at all? Don't think so. So I think he's probably going to have you start using that around multiple reactions, but it's basically just an ordinary differential equation solver that comes with the textbook, and it's pretty straightforward to use. But that's how they chose to solve for this, because they asked for a plot, and it's easiest to do rather than having to do 30 calculations. But basically, the equations you would put into that. So the main differential equations would be your design equation, and then your pressure drop, which I believe they use Y for P. Then also your equation for concentration. And then we put these in with the initial values, so like the 0.3 for C naught. You should know your epsilon is 2, your flow rate, your rate equation. When you put all that in, you get basically a plot that looks like this. Where your conversion is this bottom line, starts off at 0, increases, and then your pressure drop starts up here, so the pressure is equal to the initial pressure, and then decreases over the length of the reactor.
And the concentration
Yeah, I believe that's taken into account with Y.
What is Y? Is it just the mole fraction?
Y, so Y over here is just using the book solution, which is, I believe they used Y as the pressure. So P or P naught.
It's P naught.
Yeah, I think it's, or a ratio of the two. I think it is. Right. So, yeah. This is the pressure drop equation from the Erg equation. This one more part, 2 more parts really. So in another part, they tell you to assume it's a reversible reaction, and they give you a equilibrium constant. So instead of A goes to 2B, you have A goes to B plus 2C becomes reversible, then give you the equilibrium constant. And so with this one, you can again, you have to define it, you have to find your concentration profiles for each species, again from just stoichiometry tables. And you know that if it's at the reaction is at equilibrium, that your Kf is going to equal Kr. So the forward reaction equals a reverse reaction. So the overall rate of generation or usage of A is going to be 0. So negative Ra is going to be, so Ra essentially is going to be 0. And using this information, and the fact that they give you a Kc value, you can know, you just write out Kf over Kr in terms of the concentrations, which is going to be Cv Cc squared over Ca. When you plug in all three of these, you'll get a relationship in terms of your conversion and your epsilon. You know your epsilon, and you're just going to solve for an equilibrium conversion. So really these are all equilibrium x's, and then you'll solve for that equilibrium conversion, which you plug in the values, comes out to be 0.52. So then knowing that this is your maximum conversion, in previous conversion when it was irreversible was 0.9, your new conversion is going to be just 0.52 times 0.5. Which one? Oh. Yeah, you're right. Makes sense. I was wondering how that was. It should be squared and then cubed, and then the 1 up plus epsilon x squared. So your new conversion in the reactor is going to be, when it's reversible, it's going to be 0.47. So then if you wanted to resize the PFR and the CSTR, which it asks you to do when it's a reversible reaction, you're going to use this for your new conversion. You have the same design equations. So for PFR, you have have this, and then you also still have the same rate equation. So when you plug in plug in all this for the rate equation, you get so C and naught still 0.3, K is still 0.044. You know your epsilon, you know this new X, so then you can resize, plug in RA for up here, you can resize your reactor. So that comes out to be, what is it? I think it's 290.